Is gravity truly bending space itself, as we've been taught? In general relativity, the answer is yes. Mass and energy inform spacetime on how to curve, and this curvature tells objects how to move. In this framework, free fall is essentially the straightest line in curved geometry. And this elegant concept fits neatly with phenomena like planetary orbits, gravitational lensing, and gravitational redshift. While general relativity provides a mathematical framework that seems intuitive, it mostly ignores the underlying mechanisms. Why can spacetime be treated as something smooth and bendable? Is spacetime just an abstract backdrop, or is there an actual medium influencing this bending? Energy filament theory, however, takes a different approach. Instead of assuming a smooth geometry that bends, it starts with a sea of energy that can be stretched, wrinkled, and textured. The spacetime geometry that we observe is just the macroscopic appearance of this sea. Gravity, in this picture, is defined much more simply. It's the large-scale slope of the tension field, essentially the way the energy sea transitions between areas of tightness and looseness. Objects fall freely not because of the bending of an abstract spacetime, but because they are sliding along this slope, minimizing the total energy costs of deformation for both the object and the surrounding sea. When we observe gravity on a large enough scale, it might seem smooth and uniform, and it might even seem as though we're just looking at a curved geometry. But in energy filament theory, we never get the bending of an abstract mathematical space. What we're seeing is the way tension is distributed, from areas that are tighter to areas that are looser. Geometry is simply the macroscopic projection of this tension map. In general relativity, the assumption is that the geometry is smooth, and the curvature can be finely sliced and treated as a smooth curve. In contrast, energy filament theory posits that the tension gradient itself is not smooth, it has textures, steps, and roughness. When you zoom into regions with extreme gravitational pulls or intense curvature, the tension gradients reveal themselves not as smooth curves but as rough, granular structures. This is where the true nature of gravity comes to light, showing us that it isn't just about a curve in spacetime, it's about tension fields at work. A perfect example of this is the black hole's instant pores, which we'll discuss in the next episode. These pores aren't the result of smooth, continuous geometry, but of the extreme tension and roughness of the fabric of the sea at a small scale. They represent the microstructures that emerge from the energy sea's texture. By unifying the four fundamental forces, we realized that gravity doesn't remain a lonely geometric oddity. Instead, gravity, in this new framework, is a macroscopic mode of the same tension sea that governs everything. The strong interaction ensures that gaps within the sea are filled. The weak interaction handles the reordering of structures that are out of place. And electromagnetism governs how these textures align and move. Gravity, in this view, is the large-scale slope of this tension sea, the result of all the local interactions at smaller scales. It may seem the weakest of the four forces, but its effects are pervasive, because no matter which local phenomenon you're dealing with, it all must eventually interact with this large-scale tension slope. In this framework, the power of gravity comes from how it interacts with every other force. It is the background upon which everything else is painted. The interaction between these forces makes it the most influential of them all. Despite its seemingly gentle nature, it's always present, quietly but powerfully, shaping the structure of the universe. Next episode preview. Gravity's details aren't smooth, from continuous surfaces to tension pores. Tap follow, share it on New Physics, Clear Universe.